And hey, welcome to everybody. Welcome to our speakers. Please help me welcome our two speakers for the morning, Dr. Morgan Cable and Kalind Carpenter are with us from the Jet Propulsion Laboratory, where together they are working to develop a concept mission NASA is calling the Exobiology Extant Life Surveyor, which is conveniently known as EELs. In this joint talk, the project's science lead and principal investigator, respectively, will tell us how NASA intends to return to Enceladus with a robot named EELs, a device that will search for evidence of biological activity by doing a deep dive into the liquid water ocean that is believed to lie below the frozen surface of Enceladus. Dr. Morgan Cable is EELs science lead. She is also supervisor of the Astrobiology and Ocean Worlds Group at JPL. Her main research interest concerns biomarkers, the chemical signatures of life she is hoping to find on Mars and Saturn's moon Titan, and perhaps elsewhere in the solar system. After earning a BA in chemistry, summa cum laude, from Wilkes Honors College of Florida Atlantic University, she completed her PhD in inorganic chemistry at Caltech in 2010. Dr. Morgan has done field work in extreme environments that serve as analogs for other worlds, such as the Atacama Desert in Chile, lava fields of Iceland, and the summit of Mount Kilimanjaro. The principal investigator for the EELs mission, Kalind Carpenter, is a robotics engineer in the Robotic Vehicles and Manipulators Group at JPL, where he works, among other things, on rapid technology development and on effectors that are specifically tailored for gripping and mobility. Mr. Carpenter holds a master's degree in mechanical engineering from UCLA and has been with JPL for almost 10 years. Well, with that, Dr. Cable, Kalind Carpenter, welcome to the Greenway Talks online at Palomar Observatory. Your concept for the EELs mission is so extraordinary that it seemed clear that all of us who attend the Greenway Talks would be anxious to hear about it. We'll open the microphones and take questions at the end of the presentation. And you can type questions into the chat as we go along. But for now, I'll ask everyone to turn off their microphones. And with that, please, Dr. Cable, Kalind Carpenter, the floor is yours.
Thank you.
Thank you. We're very excited to be here. As Stephen mentioned, my name is Morgan Cable. I'm the science lead for EELs.
Yeah, my name is Kalind Carpenter. I'm the principal investigator of EELs. Pretty soon, Morgan is going to get that title, which is a conversation to itself, but we have been at this together since pretty much day one. So we're really excited to show you where it's come to and where it's going. We just got confirmation of funding for, looks like 4 years. So you're seeing everything that's led up to this success.
Wow.
And we'll be tag teaming this talk, so alternating between the two of us as we go through. But I'll be addressing most of the science questions that you might have, and Kalind will address engineering questions. So let's dive right in. First, I wanted to give you a little bit of context into why we're going where we're going and what these places are. So you might have heard the term ocean worlds before. And of course, the first thing you might think of is, well, Earth has oceans. Earth is an ocean world. And you would be correct. But what we're finding as we explore both our own cosmic backyard and start to search for and understand exoplanets elsewhere is that Earth may be more the exception than the rule when it comes to liquid water on other places. We're finding that most of the other worlds where liquid water exists don't have it on the surface as Earth does, but instead underneath a shell of ice. And so these tend to be global liquid water oceans, typically salty. The salt content likely changes depending on which body you're talking about. And that liquid water may or may not be in contact with the rocky interior of these worlds. And as we'll get into a little bit later, that may have some implications for habitability, whether or not the conditions in that ocean are suitable for life as we know it, or potentially life as we don't know it. So these are the types of ocean worlds that we have started to study and catalog. And this is not even the complete list right here, this picture of various moons of Jupiter, Saturn, and Neptune. And we'll be focusing on one of these in particular today. But I wanted to highlight the fact that just in the last few decades, with these incredible missions we've had, Cassini, Galileo, building up to future missions that we're working on, such as the Dragonfly rotorcraft that's going to visit Titan, we are learning that we're finding conditions, including liquid water and energy sources, in a lot of places that we didn't expect or wouldn't have expected maybe a few decades prior. So we'll be talking mostly about Saturn's moon Enceladus, but keep in mind that this is just one example of many different ocean worlds that we're studying and we'd like to explore further at NASA and through our various partners. So Kalind, do you want to jump in and give a few quick facts here?
Yeah, so you may wonder how you get a engineer as a PI. And where that came from is I'm a huge fan of all things ocean worlds, of definitely the, looking for life within our solar system, understanding if the genesis of life is common, really wondering about these questions I think we all care about, wanting to do my part. So what I did was collect the information from Cassini and read every paper as soon as it came out as if they were comic books. And so this is a very interesting moon. First of all, it's tiny. It's about the diameter of Texas. So it's about 0.14 times Earth's moon. So it has about 1/100th Earth's gravity. But it is whipping around Saturn every 1.4 Earth days. So this is causing tidal flexing. It's clearly putting quite a bit of energy in the system to keep this ocean warm. Now, the thing that we didn't know, and the thing that makes this so intriguing, especially for a roboticist, is it's very young at the South Pole. So it's about 1 million years old. It's got a thin ice shell. So I used to work Europa a lot. Ganymede's one of my favorite ocean worlds. You're talking 20 plus kilometers of ice on those. Here we're looking at 1 to 5. So if your job is to physically get through it, that becomes way more interesting, even though Ganymede has its own magnetosphere, and Europa with Io right there has all sorts of interesting chemistry and also this ice tectonics going on. The ocean thickness is 26 to 31 kilometers. This is far deeper than Earth's ocean. So this is also interesting because it is a lot of room for mixing and things to happen, whether this is abiotic chemistry, this prebiotic, or if this is biotic organics going on. And my favorite thing is we know there's a plume. Now, I'm pretty positive Europa has one too, but we have yet to fly through it to confirm what might be coming out.
Yes, exactly. And that is what I totally agree makes Enceladus so compelling. We started off with the Cassini mission, which I was fortunate enough to be able to work on for the last few years of that mission. It was launched in 97, arrived to the Saturn system in 2004, and for 13 years explored Saturn, its rings, as you can see here, and its moons. And this is one shot of Enceladus, which, you know, it's cute. It's the whitest and brightest object in the solar system, actually, but it doesn't look too interesting otherwise here. That changes, however, if you look at it backlit. And this is one of the key discoveries, in my opinion, of the Cassini mission, was the fact that these worlds, these moons of Saturn, are not just boring, dead, icy dust balls. They are dynamic, they're active. And Enceladus is the best picture of that. It has this plume of material that is spewing out of the South Pole, which you can see beautifully here. Now, Cassini is credited with discovery of this plume, but recently, a man by the name of Ted Strick went and used some modern digital processing to take a look at some images that Voyager collected, I believe in 1980, as it was passing by Saturn and its moons. And so here you can see beautiful shot of Saturn. The rings are not in this picture, but you can see this tiny little white blip that is Enceladus. And if you zoom in here, granted, it's pixelated, but with these modern image processing techniques, you can see that there does seem to be something in that south polar area. So while Cassini is still given credit for discovering the plume, the fact that Voyager detected it too means that it's been active for quite a while. And in fact, the material spewing out of Enceladus feeds a ring around Saturn, a tenuous ring that we call the E ring. The E does not stand for Enceladus. It just happened to be labeled, it was discovered fifth, and so it's labeled alphabetically. But this material, it has been emanating from this small moon for a long time. And you may ask yourself, well, does that mean that that Enceladus is getting smaller and smaller? At some point, is it going to go away completely if this plume continues? And the answer to that is, well, even if Enceladus, we've done some math looking at the flux, even if Enceladus had been having this active plume at the same degree we observe it today, for the entire history of its existence, it would have lost only about 5% of its mass. And so there's no reason to believe that this hasn't been going on for a very long time. Here's this is a digital animation that someone made showing how Cassini was able to fly through this plume multiple times. This was something that Cassini was not originally designed to do, but Cassini did have two key instruments that were really useful in being able to determine what that plume is made of. You can kind of picture these as a way, if you were driving in a car or someone else was driving and you were in the passenger seat and you rolled down the window and stuck your face out and it was snowing outside and you captured a snowflake with your tongue. You could sort of picture that, except you're going at a speed of about 3 to 5 times this as fast as a bullet. But Cassini was able to do that, and it used two instruments called mass spectrometers to observe both the gas and the grains that are coming out. Now, for the gas, most of that is water vapor, so H2O, but Cassini also was able to detect a few key species that got us astrobiologists and chemists very excited. These include things like methane and H2, molecular hydrogen. These are both either consumed or produced by a lot of microorganisms, things, for example, like methanogens, very small, simple, hardy microorganisms that could survive in this kind of environment. We also found simple and what we call complex organics. Now, Cassini was not meant to be a life detection mission, so its instruments were not tuned to look for biomolecules. What instead we found was that there is some tantalizing evidence for the building blocks that could become biomolecules, but we weren't specifically tuned on the Cassini mission to look for those exactly. So that's in the plume gas. Well, what about these grains, these ice grains that are spewing out? Well, Cassini was able to measure those too. And again, we found that these are primarily water ice, but a subset of them, about a third, are very salt rich, and they have salt concentrations about the same as you would expect here in Earth's ocean too. We also found what we call these high mass organic cations, or HMOC grains. These are grains that are carbon rich. They seem to have a lot of CH2, which we call methyl groups, as well as nitrogen and oxygen incorporation in them too. And so this again, this instrument was not tuned to look for biomolecules in the mass range where we would be interested. The resolution is not good enough to say, for example, these are bits of cells or biomolecules. A future mission will be tasked with that. But we found evidence that, again, is very intriguing, that the building blocks seem to be there. And so this is very exciting for us because we have this small moon that seems to have these ingredients, right? There, we see these 4 big tiger stripes that are right at that south pole, where these plumes are where these jets are emanating that form this plume. And interestingly, I don't know if you all are probably aware of this as astronomers and astronomy enthusiasts, but each world has a different theme for how the features are named. And so here you can see that the tiger stripes are named after Alexandria, Cairo, Baghdad, and Damascus. All of the features on Enceladus are named after the story of a Thousand Arabian Nights, which is kind of cool. And I went and looked up the story behind that, why they picked that. And it had to do with the fact that Enceladus was first identified by a UK astronomer. And now I'm spacing on his name, is William something. And I will look it up while Kalind is talking. But and since the Arabian Nights was also penned by a UK author, that was part of the story. And also that those, the Thousand Arabian Nights, all of those stories are very exciting. And even back when the International Union of the UPAC that was naming these features and deciding these themes, we knew that Enceladus was exciting even back then. And so that's where these names emerged from, which is pretty cool. Cassini also had a thermal infrared imager that was able to identify hotspots associated with the tiger stripe features, which again tells us that there's lots of energy emanating from a warm interior through these cracks. We were able to use that to characterize the overall flux, which is important for defining what kinds of energy sources might be available and how organisms on Earth might take advantage of that energy, whether it's thermal gradients or chemical gradients or things like that, because sunlight is not going to be accessible in this ocean. Sunlight can penetrate a little bit in ice, but once you get over 1 kilometer, it gets pretty challenging. So this is the picture, as Kalind had mentioned before, with the different thicknesses of the ice crust and as well as the depth of the ocean. We have different instruments aboard Cassini that were able to help us suss this out, things such as a magnetometer, as well as images that tell us that the crust is decoupled, it's floating, it's not attached to the crust, or excuse me, the core. We also have evidence of this hydrothermal activity down at the South Pole. And thanks to these active jets that's spewing material from that internal ocean, we have the unique opportunity here with Enceladus. We might have it with Europa too, but we know for sure we do have it here with Enceladus, that we can get ideas of what's inside that ocean because it's sending us free samples into space. And so Kalind, I think, do you want to talk a little bit more about that hydrothermal activity and what that could mean?
Yeah, most definitely. So the hydrothermal vents, I think we have some video and some other images on it. This is one of the things that's fascinated me most. So whenever we have liquid water, and we know this happens on Earth, and so this is one of the leading hypotheses for origin of life on Earth, you have the supersaturated water that's interacting with the magma. So it's heated up and pressurized, and it also gets all of the minerals. As soon as it gets out of the rock into the ocean, it's going to cool off rapidly, and it's going to deposit some of that mineral content, building up these chimneys. And these chimneys essentially work as a fuel cell. So what's going on here is you now have a pH difference on the two sides. And so with that pH difference, you're going to have electric potential, which is constantly operating through the sidewall, similar to a battery. But what's interesting here is you have your aqueous environment, and then you're going to have all of these minerals, and you're going to have energy in the system. So with Brownian motion and all the energy, everything will want to continually move around, because we know there's organics on Enceladus. And the idea was here with the organics, over time, you can start moving to things that start looking similar to mitochondria. And the interesting thing about that is it's a thermodynamic reaction to get rid of energy in the system. So this is the hypothesis that I'm really interested in, is genesis of life common? So you can see here, this is all chemosynthesis. None of these animals are anywhere near enough to the sun to actually get any photosynthesis or anything from the sun. We know life on Earth predates when we actually had much sun. The sun was sunlight. The sun was a much smaller and dimmer. We also probably had tons of hydrocarbons in the atmosphere. And then we also probably had an ice crust on Earth. And we know there was already life. So this is the leading hypothesis. This is one of the things we want to go to Enceladus to test. The other thing we're interested in is, let's say we don't get this awesome life, which I think we all hope you do find. But once there was life here on Earth, the first thing it did was eat all the free chemical energy around it, meaning life consumed out of even the geologic record at this point what a prebiotic or abiotic planet looks like. So we have no idea what actually really leads to genesis and how genesis of life, and how you go from just interesting complex chemistry to biology.
Yeah, and one other important thing to note here is that there are not just microbial forms of life, but we're also seeing crab, octopods, shrimp, multicellular large organisms that are all subsisting off of this chemical and geothermal energy, like Kalind mentioned. So these types of environments, which we can study here on Earth, can help inform our expectations of the types and the densities of life we might find. And then that can drive what kinds of instruments we might bring with us and what types of chemical tests we might perform.
Awesome. So here's images from Cassini. So thank you, Cassini, for giving us some fantastic maps and images to take this out of just the unknown. This isn't the lunar, oh, it could be covered with foo-foo dust and you sink forever. We have some good images of the surface of Enceladus.
And by the way, it was William Herschel. I had a brainwave while Kalind was talking, who discovered Enceladus. Yes, so we have these cracks, these crevasses that are reach down into that subsurface ocean. And how might we think about what the CONOP strategy would be for some type of robotic explorer to visit this environment? Well, there are different questions that we can ask as we hypothetically land on the surface, as we get close to one of these vents and go down it, and hopefully are able to reach that liquid water ocean. And so as we descend, we can start to be more robust in the types of questions we ask and in the answers that we may get. On the surface, we have a lot of these plume grains. Even though Enceladus is small and its gravity is not that strong, still about somewhere between 70 to 95% of all of those ice grains that are ejected end up falling back down onto the surface. And so just by even landing on the surface of Enceladus and collecting some of those, they wouldn't be snowflakes, they'd be more like little bits of hail. Even just by collecting those, you can make a pretty decent assessment of what is present in the ocean. But there could be some processes that might, say, enrich or deplete or modify the composition of those organic molecules or other things that are in those grains. So there may still be a question of, well, is this truly representative of the stuff that's in the ocean? Some things might have evaporated or boiled off in the vacuum. If there are cells, for example, floating around in that ocean, could they survive the physics, the sort of tremendous forces as it's being shot out of this plume? And so that's why we would like to not just address these life questions on the surface, but get into that vent and be able to reach that ocean where we can sample the liquid directly, because then there's no question about processing or changes to that sample between when it was in the ocean and when you were able to ingest it into your instrument. And there are all sorts of questions that we can ask. Presumably, we would do some chemical tests. So we'd search for specific molecules, again, trying to be as agnostic as we can from Earth life, right? We don't want to go and look specifically for DNA, for example, because that's very Earth-centric. Maybe this life originated with some different biopolymer, some other way to store information. So we would try to look for, say, similar large molecules with repeating units that use a similar type of alphabet as our DNA molecules do, but perhaps made out of different stuff, but still would follow some of the basic rules of chemistry that would exist in a liquid water environment. If we were going to, say, the hydrocarbon lakes of Titan, we might look for different things there because the solvent is different. But here it's still liquid water. So some of those basic rules, the same kind of molecules that dissolve in our oceans, will dissolve here. And so following those basic rules, we would look for the same type of chemistry. We would also want to search for what we call morphological biosignatures, things like cells. So not just the chemical components, but actual direct evidence of that life, hopefully swimming around. That would be really amazing as well. And so these are the kinds of science goals. And based on that, our assessments of how dense the life is in our own Earth's oceans down in these energy limited environments that we see, these hydrothermal vents, then we can say, okay, we need 7 cc's of ocean liquid because we can be sure if there is a cell in there, that volume's enough for us to be able to say for certain whether it's there or not. Those kinds of things then inform what kind of instruments and what kind of sampling systems we would use.
How can you not be inspired and find that worthy of putting your career behind coming up with solutions for? Thank you, Morgan. I love this. You can tell.
Me
but
too.
This is why, right? These science questions. Now I'm going to get into some of the technical how. On the right and left, you actually see images of Enceladus's surface. Both of these are from the skeet shoot. So this is when we got the closest to the surface with Cassini on a flyover. But each one's pieced together differently. So on the left-hand side, you can see here, more if you go to the next slide, you see how it looks like it's just a crack, just an open crack. And then next to this, I illustrate how you see how it's just a parallel crevasse. So this is one of the leading hypotheses by Kite and Rubin. And the feeling here is it's a crack that opens and closes, not fully closes, but there is a tidal flexing essentially, and boiling is the boiling of the water because the low pressure of space is leading to this ejecta. Then on the other side, you can see this is more of the Carolyn Porco one where it looks like everything is circularized. So on the next one, you see the circles actually around each of those locations. So right, not as an engineer, not wanting to get into the processing and the debate, the interesting thing is, okay, we can bound this problem. I don't need to know exactly what it is as long as I know the bounds in which we need to operate in. So on the next slide, Morgan will tell you more about the physical processes that could be driving these two.
Yes. So as Kalind mentioned, there seem to be, based on our observations from Cassini, 2 different models that fit our data. One of them says that there is just an open crack, a crevasse that goes all the way straight down to the ocean, and it's about 5 meters wide. And as Enceladus orbits around Saturn every 33 hours, that may sort of open and close, not close completely, but have this pumping action that causes the liquid to sort of move up and down. Now, in both of these, though, you can see the liquid fills the majority of that crack, and that's due to hydrostatic pressure, just based on the weight of the ice pushing down. Any liquid is going to go up and fill about 90% of that ice thickness. And that's good news for us, because that means even if this is 5 kilometers thick, we only need to go down 500 meters, a tenth of that, right, to hit that liquid. So that's one theory, and that's great. That's easy. All sorts of robots could handle that. The more stressing case is what you see on the right here. The other model that fits the data we have is more similar to some volcanism that we see here on Earth. Now, again, with magma, not with water, but some of the same physics applies, where you have a bulge, a chamber, and then you have a choke point. And that choke point could be as small as tens of centimeters. So much, much smaller than the 5 meters that we were looking at on the left. And at this choke point, now you have, you're at the triple point of water. You've got freezing, boiling, all sorts of things going on, and supersonic flow afterwards. And so the idea behind Kalind's inception of EELs was to be able to design something that could handle either of these scenarios and still be able to go against those forces of the plume pushing up, so that we can still reach the liquid, regardless of whether it's an open chasm or has this constraining choke point. And
Excellent.
Kalind, I think, is going to summarize this part. Yes.
Yeah, so you can see here, so what I did, and we have another variant of this that actually has all of the papers that these were pulled from. So we have the mass flux, we have exit velocity, number of vents, we can calculate the range of the dynamic pressures that would lead to what we observe. We get ice thickness, shape, plume throat, particle size out of it. So we have everything bounded. We have an envelope around what we need to do. So to do that, now if I take this into robotics and I started thinking about it, we need something that has a variable diameter, essentially, right? We have this place where you could be, most likely 2 millimeters isn't super likely, but probably 7 centimeters, 70 millimeters, up to about 150 millimeters. This is in your worst case scenario. If it's the Fisher one, gravity doesn't dominate, somewhere around the 1 meter to the 0.8 meter. So we need something that is somewhere between 7 to 15 centimeters when it's the small diameter, and as big as a meter on the large diameter to be able to touch the sides of these structures. And as you probably tried at some point in your life, pushing on the sidewalls of a hallway, you were able to shimmy right to the top as soon as you could push onto the sides. Didn't matter if that was smooth, if it was glass, what those walls were made out of. As soon as you could get the force between your two hands, you could overcome the gravity acting on you. So in the next slide, we go into one last thing we really want to talk about. So we understand that this is likely a habitable ocean for Earth life. So we do not want to bring Earth life with us to take over or inhabit this world. So this whole entire thing has been designed with a method to ensure that it is what our medical industry considers completely sterile. So for the inside, we actually want to build each of our actuators. This is one of them inside of a vapor hydrogen peroxide bath to ensure there's no life living. Even the way that we build up the circuit boards, we can actually leave them at pressure and temperature long enough to ensure there's no viable life. So even if over time the circuit boards were to rupture, we would not contaminate the body. So there's more work that needs to be done here, but you can suspend disbelief on our ability to go there, as in we will not go until we can ensure the pristineness of this body after we enter it. In the next image, you'll see the secondary part of that. The other part, even if we have no contamination on it, you're worried about recontamination. So the nice thing is we have 8 to 12 years to get from Earth all the way to Enceladus. And if we have UV and IR sterilization, we will have more than enough dose to ensure full sterilization on the outside of the robot previous to landing on Enceladus. So now let's introduce you to the concept. So landing on the South Pole of Enceladus, we have the Exobiology Extant Life Surveyor, or EELs robot. This is designed to be a fluid or fluidized media robot. So these particles at 100th gravity likely fluidize as we move through it. So using counter-rotating screws, Archimedes screws, this can push itself through, even burrow. That's a sublimation anchor. We have some videos of it in the backup, early work that I did. Once we anchor, we put the front of the robot in. At this point, it's a robotic arm with a sampling system. This is when we get the most pristine sample and as much sample as we need, because we can stay there until we get it. We've probably at this point done a very good job of characterizing the ocean below, understanding it, but to Morgan's point, we don't know the processing, the provenance, what happens with this rapid depressurization. So this robot's designed to push onto the sidewalls. So first it would actually repel if the force balance allowed it to. But as soon as gravity doesn't dominate, it pushes on the sidewalls and it becomes the self-driven corkscrew with this active skin that's constantly maintaining its force on the sidewalls as it progresses downward. The nice thing about this, so this is your Chitin Rubin open crevasse. Now, if this was more of a moulin or not really moulin, but something more similar to that, where it's a circular geometry, it's probably more like you'd get a volcanic vent where they will circularize as the magma cools, freezes on the sides. So at this point, it becomes a self-driven screw. So now there's less mechanical disadvantage, and the robot is designed to be able to power through the forces that you may find, or the forces that could be the input side of what Cassini was able to observe. As Morgan pointed out, right after that, you're near the high tide point where either the tidal flexing or hydrostatic pressure will have pushed the water up near the surface. Now, EELs swims through the water, still using those counter-rotating screws, more as propellers at this point, to see if it swims alone.
Oh, I get goosebumps every time I see that.
Excellent.
And of course, yes, you have to have a great acronym, and Kalind definitely rocked that when it came to EELs. This is part of many different mission concept studies. We've looked at versions where we could have multiple EELs robots able to access different parts of the surface and the crevasse. Because what do they say in Contact? Why build one when you can build two at twice the price? So redundancy certainly would be useful here, especially going into these unknown environments. But we can do a lot with one or multiple, depending on what the architecture can support. Kalind, did you want to say anything more on this slide before we get into a little bit more of the mechanical detail?
Well, the big thing here is there's multiple architectures. So you see this one is landing if we were in the polar night. So Saturn, when we, you all know. So in this case, this was looking if we were to land after the South Pole of Enceladus was not facing Earth. And so we have an orbiter. You can also see that the first thing the robot's doing is just being a robotic arm. So getting a sample, then as it leaves the spacecraft, it gets outside the contamination zone of the lander. And then it also works to look to see if there's concentric rings where heavier particulates may have fallen out of the vent flow. So there's a whole lot of really interesting surface science before we ever get to attempt the subsurface.
Yeah, that's a great point. And so this is nominally what EELs would look like. And Kalind, I think you're going to step through. I'll just keep clicking through. So you just let me know.
So it's about 4 meters long, and that gives us more than your 1 meter circle. At the front, it's exteroceptive, or this is your remote vision, so like our eyes. So we have a bunch of different ways of seeing the world for the robot, including, underwater using sonar. So all of those are housed in sensor fusion. After that, currently it's identical modules. We would probably actually make these with specific force profiles to reduce mass in the future. And now that we know we're funded, we'll likely do that with our 3.0 variant of this. But by having all these identical modules, we have redundancy throughout the robot, which is really nice in case issues come up. And actually, we find we can build about 3 of these for less than the price of building 1.5. So there are economies of scale from the serially replicated aspect. Each of these have their own sensors. It is distributed control. There's a lot of really cool technology that's supporting this. And as far as I know, it's one of the first the first use cases for this active skin propulsion, where even though this is snake-like, it is not operating like a snake. So we're kind of cheating in a snake when it's most efficient in unconsolidated media going up slopes, goes into a sidewinding movement. The screws are essentially allowing our Revolute actuators to just enforce that. And then we have the shape actuators, and pretty soon we'll get into more of that. That's followed by the science payload I think Morgan will tell you about.
Sure. Yeah. So we would have one or more dedicated modules to house an instrument and likely a sampling system as well. Currently, technology development efforts are looking at how to sample from that solid surface material whether it's loose, the fine grain sort of sand-like hail that I mentioned before, or if it gets warm enough where it can sinter, so you can have more of like a creme brulee layer. There are different ways that you could sample either of those. As well, when we reach the ocean, just being able to sip in and hopefully filter a lot of that liquid to search for things like cells. So there are all sorts of different payloads. We're working with a lot of different teams to be able to meet the form factor for what eels would look like, as well as the power and other thermal considerations. But there are certainly a lot of different things that we could do depending on how many different science payload elements that we would like to include.
And the power management, this is one that we're just finishing up right now. That's twofold. One, we have kilometers of this tether. So we are ordering the first tether right now. So the first one will be about 6 millimeters thick. So this is structural. This is also our fiber optic comms. This is also our high power over tether to make it efficient over distance. The power management, the biggest issue there, other than the down convert of the high voltages, the 80 volts the robot needs, is when this robot stops, we have the inertia of all of these screws that then create a bunch of power, like your regenerative braking on a car. And we have somewhere we need to shunt all of that power. So we have a variant of that right now. And this whole robot you're looking at here will be together in less than 2 months. We'll have 2 of these modules actually with the autonomy stack operating on them in 2 weeks. So it's all moving along quite nicely.
It's all coming together, literally.
So yeah, here's an earlier version that we built. So this was during COVID. So the reason why this robot isn't fully together is because it's been in boxes since August 2020, and we just got funding renewed and access to the lab. But we were able to 3D print out a variant of this that one of our interns was using in his room. And so you can see this linear mobility we were talking about. You can also see its ability to describe different shapes, so these figure eights. After that, it's going to go on to this ability to conform to the sidewalls, right? So the robot, this is what we call proprioceptive or tactile sensing versus that exteroceptive. So that's all of these sensors and torque sensing that we've got the robot to be able to do, so that it doesn't really need to know everything around it. It just knows it wants to push with a certain force outwards, and it pushes. And if it hits a wall and it is going to push harder, it lays off that area and then pushes hardware somewhere else until we normalize it. You'll see that in a moment. Here is some of the vertical climbing. So this is with just a circular cross section.
And
then,
Kalind, maybe you mentioned why we're demonstrating going up instead of going down.
Definitely. Well, we're going to get to a slide on that, but going up against gravity is actually about the same order of magnitude of forces as going down against the vent flow. So for Earth testing, we don't need the gravity offload to be able to do pretty good analog testing. We just go up against gravity, and then the forces are in line. And because this is supersonic flow, what you end up having is you have a bow shock on the front, which means a pressure difference. That pressure acts over the whole surface, which is similar to gravity acting at the centroid of that area. So that's fantastic. The other thing is, if gravity doesn't dominate it, it means the static pressure is actually above the triple point of water for, well, just water anywhere in the universe. But for Enceladus, that means as we're going down, the ice is heated and pressurized by that water vapor. So on Earth, in our atmosphere, going up, pushing against ice, right? If it's -15 to 0C, we'll be right in line with what we'd expect there. Now, there's a bunch of other things that are going on to get there, right? We're going to have slopes, we're going to have cliffs, we're going to have sparse rocks, we're going to have undulating terrain, gaps, crevasses, chimneys, water. So we broke all these down into what we call shape primitives. And in the next one, you can see how this 3-dimensional line with this active skin can start describing all of these different modalities, these different gates, ways of essentially walking to be able to get through all of these areas. So you can see how it can move like a snake. It can do side winding, or it can just move forward and backwards with the screws, side to side. That differential drive one, it essentially becomes 2 tank treads and has a little bit more of your traditional side-by-side maneuverability. You can see that wheel mode on the bottom left. So that's one of the most efficient, where these screws, when they rotate, progress you forward by 1 full circumference. So just like your wheels rolling. The screw mode, now we only go by the pitch, so it's less efficient, but we have this very nice ability to deal with the constrictions. And so you see that in the cone and definitely in the choke point, how the robot definitely has to go into that driven screw modality. So I'm actually going to leave on Tuesday to Trondheim, Norway, where we're going to have students spend 24 hours figuring out which one of these is the best solution to get over some of those terrains. And we're going to have the simulation at 100th gravity, where this thing can actually operate like a spring and float around. And I can't wait to see the creativity the students come up with to really fill this trade space out. So now you can see the ability of the robot to conform, right? So other than these different modalities for moving, this line to spiral is really interesting, because what we can do is we just rotate all of the rotational joints, and it works very much like a cam to be able to push into the sidewalls very strongly. And then you see we can effectively change the diameter and this differential transition. Excellent. The next slide, this is that testing equivalence, where you can see I went through and did the calculations using some of the worst case scenarios for Enceladus, not the worst cases, but some of the worst cases for, a 10-centimeter throat. And that was right between your 7 and your 15, actually a little bit on the low side. And we found the Earth mass equivalent in the force for the projected area of this robot is only 60 kilograms. Right now we have about 100-kilogram robot. I know it was 80 when we made this slide. Now it's gotten up to about 100 kilograms. So when we show this robot's ability to go up against gravity, it's actually almost, twice the reaction force and ability to progress up against gravity than what we hypothesize we'll need for Enceladus.
Perfect. Yeah, and so of course we have to do testing on Earth, because it's really challenging to get over to Enceladus. We want to make sure that everything works. And so in addition to this mechanical testing, this proof of concept type of work that Kalind describes, as a scientist, excuse me, I also want to do some cool science too. And so we've been working with a lot of cryosphere and Earth scientists to try to determine how a robotic mobility platform like EELs could address some key Earth science questions. And it turns out that there are a lot of really gnarly places in glaciers across the world, but we've been working specifically with some teams up in Canada to access places that may be very dangerous for humans to go, where we can collect samples or drop sensors to study how that glacier is evolving over time, the effects of global climate change, and otherwise characterizing the physical and biochemical properties of what is inside that glacier and also underneath it in what's called the subglacial channels or subglacial conduits. And so these are unique ways that we can utilize this mobile platform to be able to access places that are dangerous or otherwise challenging for Earth scientists to reach. There are a ton of other applications as well. We won't have time to get into it in this presentation, but EELs can do everything from helping with what is it? If you have a natural disaster and you might have people trapped underground, EELs can reach places and have sensors to be able to help address that. There are ways that you can utilize it for resource exploration and all sorts of different things. But from a science perspective, we wanted to do something focused. And so we're working with some teams in Canada to reach Athabasca Glacier for a lot of this field testing. And we're really excited about that. Now, I know we're getting close to the top of the hour, so I think Kalind's going to talk a little bit more about some of the robotic actuator capabilities, and then I think maybe we'll skip and open up for questions. Does that sound all right, Kalind?
Yes, definitely.
Okay, cool. Cool.
All right, so the big thing I wanted to show is we have these different complexities of environment. So without being able to see ahead of us, we can get up to about level 3. So that's what we demonstrated. Level 4 is where we want to go. So that's why we're putting together, actually, I'm up in Mammoth, and in the back room, one of my colleagues left our whole sensor suite of cameras to be able to try out in the snow, but we need to be able to map it. So in the next slide, this is where I'll get into the autonomy needs. So we need to see the world. Just real quick here, the first robot, at least the one that we're putting together right now, is a counter-rotating gearbox, which is a first of its kind that ends up with about 95% efficiency. And it took me a while to really get the math here, but by dumping the reaction force into something that's moving instead of a static wall, the efficiency goes up. So some of the technical accomplishments of this team I want to bring highlight to as well, because it's fascinating all the way down. In the next slide, you can see this ability to cam. So this, in this case, what we're doing is we're leaving all of our planar joints at exactly the same angle, and then we just change the rotation. So you can see in those top squares how effectively the diameter of the robot's changing, but the screws are always what's in contact. So we have this ability where the length of the robot changes, that effectively changes the diameter of the robot, but we maintain that active skin or screw contact on the walls at all times. Then in the next slide, we have this rate of traverse. There's a lot of people who ask, how does this compare to the SUVs or helicopters? We actually have this, we're working on that right now as well. So in 1.25 Mars years or 2.5 Earth years, the Perseverance robot has to go 15 kilometers and take 20 drilled samples. What we're looking at doing, and this is why we need the autonomous aspects, is in 16 Earth hours, we want to go 3 kilometers. The reason for this is the full thickness from the top of the ice down to the bottom of the bulge chamber is 3 kilometers. As Morgan pointed out, we probably will never need to go more than
500 meters.
meters,
Yeah.
right? But to make people happy, we showed that actually the same operation speed at about 4 centimeters a second is 3 kilometers in 16 hours. So if we have a robot that has the power and the autonomy ability, then it can actually do it. No, there was some scientists that early on, because remember we started this when Cassini was still flying through the Plume, where they thought that the Plume or the vents may close. And so if the vents fully closed, you were worrying about crushing the robot. So we wanted to show that the robot could actually get through, get through the whole entire crevasse if it was opening and closing before it would get crushed. So it's a little bit history, but this is one of those things that it stuck around and the team's still building to it. So the capability will still be there, but you're right, we don't actually have to do it. We're hoping that this will be a radioisotope driven mission. All of those will only be on the surface. They won't go down to the ocean where they're not allowed by planetary protection. So we're actually hoping this is, you know, somewhere between Cassini and Voyager, where we have 10, 20 years of operation, especially once we're in the ocean. It doesn't take a lot. Another thing that people ask about, well, what if you can't see, right? What if you have things freezing? Well, if we do have obstacles because we're moving down through the flow, those obstacles will actually work to block the flow. So we've been looking at doing this flow sensing. So you can see in the next one that Morgan just went to, this is someone sending an endoscope down Old Faithful. So we're aware that you can't see very far ahead of you, right? There's going to be occlusions. There's going to be things getting right in your camera. Are things going to freeze the lens? We actually have a test we're doing in the next couple of weeks to find that out. And so as you go down, you can see this is not where eyes work super well. That's why we have this backup of being able to do everything by feel. And so we're actually pushing what's called proprioceptive robotics quite a bit by this effort. And then in the next slide, you can actually see more or less how we think this would work from an operations standpoint. So we're building the operation environment right now. You can see the robot has the shape that it's in as it's going down. And this one where you see the screw, you can actually see which ones are in contact. So we feel which ones are in contact. And right now we're actually looking to see not just which one's in contact, but where the normal contact is happening. Because what we really want to do is be able to change the vector that we're pushing outward. So the reaction force all comes inward. Then you can see the vision and you can see which one of those poses or gates it's in as it goes down. And this was built on, this is a front end to the back end of the control software we use both for the helicopter and the rovers on Mars. So we wanted to show that we do have an intuitive way of working with this robot. The current one that we're building right now, that top joint that you see where the head swings back and forth to assess the flow, it's now a universal joint, so like your shoulder. And so if you were to teleoperate this, if it didn't have to work autonomously during the dynamics of the flow, because you've got about 4 hours round trip, 3 hours round trip flight for your communications, what happens on Earth or once you're in the ocean, you can look around with the head anywhere you want to point, and then you just drive forward or backward. The robot takes you there and it figures out how to make sure everything behind it goes through the same point in 3 space. So it's going to look really cool as it operates. So that's the Earth robot we're building with our goal to go to Enceladus. All right. Do you want to sum it all up, Morgan?
I would be happy to. So, and I hope we've convinced you that Enceladus is one of the most astrobiologically compelling destinations in the solar system, in particular because it looks like we can access the subsurface ocean without the need to dig or drill. We think that robotic capability that EELs enables will be able to get us there to that extreme environment and hopefully provide evidence for the first time in human history that we are not alone. And so with that, we are standing by to answer any and all questions you may have. And thank you very much for your time and for the invitation to speak today.
Kalind and Morgan, thank you very much. That is truly remarkable. Make no small plans, dream no small dreams. Wow, that's really impressive.
Well, our motto is "Dare mighty things" at JPL. So,
which is kind of close to make no small plans, dream no small dreams, which is
yeah, and also make cool T-shirts.
Excuse me. Oh yes.
Yeah, you can see. Yeah, that full robot.
I would like to point out, as we're doing the questions, that we mentioned Cassini at a couple of points in here, and in some ways this starts from some of the observations Cassini made on June 4th. Dr. Linda Spilker will be here. Yes.
She's our champion. We
yeah, she's actually a science advisor for this mission concept as well. So she's fantastic.
She inspires so much of this. It's so good.
And she takes the position that Cassini is still making discoveries, still going into the data, still finding things. And she'll be here to talk about, title is Surprises in the Saturn System, updates on Cassini's continuing discoveries. So that's coming up. Questions? You can unmute or whichever, and let me open the floor for questions. Well, yeah, go ahead.
Let me ask what should be a simple question. You were seeing complex hydrocarbons in the jets coming out of Enceladus. what's the relative abundance? I mean, is there just a little, or is there an obviously there's enough to make you think it's worth going there to do, but what's the relative abundance and how might that compare to what you would see on the Earth?
That's a great question, Tim. So Cassini had two instruments that it used to study the organic content of the plume. One of them was called the Cosmic Dust Analyzer, CDA, and that's what analyzed the grains. Essentially, how it worked was that it had a rhodium plate, a metal plate, and when an ice grain came in at about 5 kilometers a second, it would impact that plate and essentially go poof. It would vaporize and ionize a lot of the molecules inside. And that's how we were able to measure the composition of the plume. It also means that for each ice grain that came in, we got a unique mass spectrum. So we essentially got a fingerprint of each ice grain that hit. And in doing so, CDA was able to identify a bunch of different types of grains. So about a third of the grains that we saw were pure water ice. So not super interesting. We think they formed from condensation of water vapor as it was going up the column. So those are, less astrobiologically interesting. Another third of those grains were very salt rich. And so that's where we understand that there's a lot of sodium chloride and sodium bicarbonate in the plume. The final third, turns out, are the subset of those are really organic rich, but the others also contain some lighter organic molecules. And in that subset of those grains, we found about a 1% by mass or larger organic content. So again, Cassini, this cosmic dust analyzer, it's a time of flight mass spectrometer. So it measures how long the ions take to get somewhere. And so for heavier mass things, like some of these organic molecules that move more slowly, your mass resolution gets really poor. And so we weren't able to identify, for example, if those were specifically amino acids or bits of proteins or what have you. But we do know that overall that organic content was about 1% by mass or higher. And that's a pretty significant value. So we're using that to help us constrain what our measurement requirements and instrument performance requirements would be for other much more targeted techniques.
Do you think it's likely there'll be a precursor mission before EELs to refine some of those numbers, or are you just going to go there and see what happens?
I am working on a proposal to NASA's New Frontiers program that would be that precursor mission, yes.
I think we don't need a precursor.
I don't think we need one either.
Like I don't need more information to go for this. And the opportunity cost of sending anything else first essentially means none of us may live to see it. So I am not a fan of precursor. I feel Cassini.
Cassini was the precursor. Yeah, exactly.
Exactly.
You can't be that old.
Well, so the problem is 12 years to get there, and it normally takes 8 years to build. So if we select anything else, it's minimum 20 years till they'll fund anything else. And it's 20 more years till it gets there.
Well, we could do 7. I think on the right rocket, you could get there in 7. But yes,
that's true. You're right. You're right.
It depends on a lot of factors. And Robert looks like he's had his hand up for a while.
Thanks. First of all, I just wanted to commend the two speakers for this talk. I spent a lot of time at sea. I was a fisheries biologist, and we used to have a lot of talks on the rail about space exploration. A lot of people thought, why is so much money being wasted on this? And I think it's just unbelievable that we're coming full circle, that we're going to look for life in an extraterrestrial ocean. That is so sweet. But this brings me to my point. We've deployed a lot of things from ships, and it didn't matter whether it was cheap or expensive. There's kind of an old saying about if you put it over the side, you better be prepared to lose it. And the thing, I think the probe is so ingenious, but the thing that worries me is the tether. And the tether on our gear at sea was always the weak link. And whenever we lost something, and it usually had to do with the tether, either it tangled on the bottom, something, it slipped on the surface, on the pulley, there was some sort of fatigue. And I was just wondering how you're going to approach the tether to try and decrease the chances of some sort of cable failure?
So this is cool. The tether guy is one of our teammates. It's one of the key focuses that he's been looking at. But these are all Kevlar wrapped. So it's really interesting how the buildup is. So you have the Kevlar wrapping, then you have the copper around your fiber optic center, and the copper with the ohmic heating actually works to heat the glass on the inside and to ensure that you don't overcome its bend radius to get microfractures. So it will not be a very flexible tether, but it's very, very thin. And because you have a woven outer jacket of the Kevlar, that's actually what takes the force, and then abrasion means it doesn't lead to a cut that will be able to continue. And then when it's under load, it'll grab on to all of the other strands. So the robustness and survivability is where I think I put in the chat that tether failure is likely the end of this mission. But we're trying to make sure that that tether failure is, if not on the order of years, definitely, at least a decade. And we have the ability to test that. And we see that done all the time on Earth. But you are right. The tether is the weak link by a lot. So we're using these crazy materials to be able to do it. The coating for the wire also is actually really robust because you're worried about these partial pressures that give these coronal effects that lead to degradation of the tether over time. So actually even down to the material science that's gone into the coatings of them for both longevity and hindering that. Also actually add a structural component, which is pretty good. So they're all polyimides. So they're all these really low outgassing. It's what we use for our astronaut duct tape and for all of those blankets that you see on all of our spacecraft. That turns out to be one of the most stable things also for high voltages. And so the whole thing's essentially coated in that within the Kevlar, which is related. Instead of being a polyimide, I think it's a pararamide. And so that's your bulletproof material that we use all the time. So fairly darn robust when you're talking about the forces that we're talking about, because you're talking about a person hanging off of it, right? And so this isn't ridiculous forces. I'm sure when you were in the Navy, especially with a drag, you guys were probably seeing well over 1,000 pounds of tension and all sorts of crazy stuff going on. I know fishing nets can just be ridiculous. We're talking about just a person hanging off of this, and most of the time not even hanging, right? So a lot of time it's just under its own weight, the 100th gravity. My worry though is the plume forces getting it to move back and forth is abrasion on the surface. And so that's why having that Kevlar outer jacket is so important. But if you're harder than ice, the ice can't really damage you. So that's kind of what is, and someone put in the chat asking about the screws as well, right? We've been looking at the hard materials so that, they'll likely dull a little bit over time, but in general, if something's going to give when they come into contact, it will be the softer portion. So we're have some really good material scientists on it. And let me tell you, I'm finding a huge respect for what they do.
Yeah, and it's interesting, Robert, that you brought up your work at sea, because what we found in recent years is now we are starting to tap your community for science and engineering expertise. So we've got a lot of oceanographers, marine biologists, marine scientists, and cryosphere scientists now that we're finding that oceans are not exclusively an Earth thing. So it's very cool, this joining of the planetary science and Earth science communities, which is very cool.
Galvanic corrosion is such a real issue. First melt probe I put together, we tested it and found some galvanic corrosion. We will not ever make that mistake again. Oh, it is real. It's so crazy.
Yeah, there are a lot of really great questions in the chat. Kalind, did you see any that you weren't able to address also in the chat?
Oh, so we are hard. So right now the robot is hard anodized, and then the screws are diamond light carbon coated. So all of the metals are actually coated that come into contact. We have Teflon seals. The Teflon can handle all the temperatures. We just need to make sure it doesn't cold flow at any time. So if it's actually under pressure and gets to certain temperatures, it'll basically take a new set. So we need to make sure that, you know, we'd be fine during cruise getting to Enceladus, but once there, we're not too worried about it. Let me see. Yeah, that's one of the cool things. So just for cost reasons, we didn't jump right to steel. We did aluminum because we're still figuring out the geometry. The group figuring out the geometry and doing all the simulations and modeling is amazing. And we don't really understand like ice skating, right? We don't understand ice skating. We've been reading ice skating, watching the Olympics is so cool, but you can go out in Canada at, you know, -35, -40 Celsius, which is -40 Fahrenheit, and still ice skate, and it works. But you know there's not any water essentially on it. So some people think it's pressure melting and this like hydrogen flowing over the surface allows ice skates to work, but it could be that crosses over to actually be the ice is shattering and becoming little ball bearings, and you're basically skating on that. But every little kid does it. But as scientists, we have to understand it. So we're figuring it out. But it's one of those things where the robot just keeps working. And we look out in life, we look out for bio-inspiration, and we see that this stuff works. But now we're really trying to figure out how, so we know what we can capitalize on most to ensure for each amount of force we push into the wall, we're getting the most amount of grip. We call it the grip coefficient. And so that's what we're really pushing right now. Awesome.
Well, I've got another question that I might have missed because I had to leave and couldn't hear everything while you were talking. But when you finally get down into the ocean and now you're looking, I mean, it's an astrobiology project, right? So you're looking for life. What specific molecules are you looking for, and how close are they to an organic process? Like I assume you're not going to be looking for like DNA and RNA or something incredibly specific, but what is it you're going to look for, and what do you hope to get out of it?
Okay, so this is something that's been in work. There are actually a lot of NASA organizations, research coordination networks that are working on defining what they call agnostic biosignatures. So classes of molecules, other morphological signatures, things that are not Earth-centric, but still would be indicative that life was there. And I'll give you an example, Tim. Amino acids are abundant. If you look at a cell, they comprise about 50% of the dry weight is amino acids and proteins. They're also found abiotically, right? We find them in meteorites all the time. But the key difference is in life, you tend to utilize all sorts of different amino acids. They are strung together, and then as they fold into these complex, large molecules, they make proteins that have certain functionalities, right? They will grab onto metals that are active sites for chemistry. The way that they fold and interact determines a lot of these binding sites for how a lot of the cell functions that are keeping us alive work. In comets and meteorites and things like that, we tend to only see the simplest amino acids, things like glycine and alanine that are just thermodynamically, they're like the easiest to make. Life can't do a lot of interesting chemistry with just a long string of glycines. And so when you find that life has altered an environment, now you will see more complicated amino acids like histidine and tryptophan and serine that are found in much greater abundances than you would typically see them if only abiotic stuff was happening. And so it's not the presence of amino acids or not that is the biosignature, it's how much of different types of those amino acids are there. Does that make sense? And so that way, even if Earth, this alien life uses different amino acids, it doesn't matter if they're different from Earth life, just the fact that if we find complicated ones in really weird great abundances, that would still be a biosignature, even for life that was very different from Earth life. And we can do that with other different molecules that we expect an organism might utilize. For example, we're still in an aqueous environment. right? And we could presume that life would use some other type of molecule to house its molecular machinery, to form a cell membrane. Now, Earth life tends to use phospholipid fatty acids. We use these long carbon chains because those are non-polar, right? And then they'll have a fatty acid end that is polar, and that's what forms those micelles, the lipid bilayers that form our cell membranes. Okay, well, if we're in an aqueous environment, we could assume some similar molecule might be used. Now, it may be a different chain length, but chances are it's still going to be made out of carbon, hydrogen, nitrogen, the same elements that are abundant in our solar system. It's not going to be made out of like tungsten or something weird. It's going to have the same sort of reactivity and be around so that the organisms can eat it and use it to make their bits. And so we would look for, say, abundance patterns of different carbon chains. And if we see Earth life uses 16 and 18 carbon chain lengths, plants use C20 or C22 for some weird reason. And well, I know the reason. I could get into it, but we're already over time. Sorry.
Yeah.
But we would look for those patterns. And so if you look at carbon chains here on Earth life, you see big peaks at 16 carbons and 18. We don't use 15 and 17 because we added on in even units because it's the pyruvic acid is how you add it on in the citric acid cycle. So we would look for similar patterns that are different from abiotic ways of making long carbon chains. That's another example. There are a few more, but I'll stop.
Now, I've heard of the lipid bilayers forming in prebiotic chemistry spontaneously. So that would be an interesting thing. So did it ever occur to you in your wildest dreams to do something like Perseverance is doing, suck up some of that water and crawl back up to the top and sit there with it so somebody could come along and grab some and bring it back to Earth, and a sample return mission from Enceladus, basically?
There have been multiple sample return mission concepts proposed and studied. In fact, you might not even need to land, right? You could just fly through the Plume a whole bunch of times, grab a ton of stuff, and then come back. Still, the round trip is going to be at least 14 years. And you have to guarantee that that sample for the 7 years from collection to coming back to Earth, that it hasn't been chemically modified in any way. It hasn't been contaminated. And so it's certainly something that we will likely continue to pursue and study. I think just as we've done with Mars, a combination of in situ science as well as sample return is really going to be needed to address a lot of these questions to the fidelity that we would all want.
Good.
So write your congressman, tell them more money for NASA, please, so we can do all of these things because our budget is not very big.
My congressman doesn't listen to me.
Well, maybe we can get a few more letters to head their way.
Everybody right.
Yeah.
Well, we've had a lot of questions in the chat. I'm not sure we've gotten to all, we've gotten to most. I don't know if we've gotten to all of them. One particular, Irene, you had a question earlier. Do you want to bring it up?
Sure, but I think it got answered in the chat. I was just wanting to know if you were able to time the arrival so that it was at its warmest point.
That is a good question. So Saturn's year, its orbit around the sun is 29.5 Earth years, right? And so that means that there are going to be a couple of decades where the Enceladus South Pole is in darkness. That does make things more challenging. And in some respects, it might be nice to get there when it's warmer, but also I don't want to hit pause on my mission for 20 or 30 years just so those conditions are right. I'd rather over-engineer the crap out of it so it could handle it no matter what. And as we all know, some NASA missions do get delayed because of funding issues, because of politics or things that are far outside of NASA's control. And so as we're approaching this problem, yes, we ideally would like to land in the most optimal conditions, but we're going to design to land in the least optimal too. And Kalind, if you want to add on anything, please do.
I love the idea of civilization class missions. And I think that all of us, I know that a lot of it might just be chatter, but as someone who was not alive for Apollo missions, but was very much inspired by the space shuttle, I love this idea of the Artemis generation, right? This idea that we'll have our turn as well. And you look back and we're talking about Voyager, and we're talking about all of these things that are older than I am, not much, but just, and we want our flagship, our first of its kind. We want our things as well. And this idea that it's all been done is patently false. We really want to show what we're capable of. So this heritage, fly what's flown before, let's follow this 2 times a decade cadence, anything else. I've never really bought into it. It's not something that I think is good for the public that pays for this end of day. I don't think it's inspiring people into, STEM as much as it could and should. And it also means we don't provide the positions or the career satisfaction that comes along with it, right? See, Morgan is one of the most amazing astrobiologists and ocean world scientists in the world. She gets to do this because she's on all of them, right? So
Not
go
all
into
of them.
science would be one thing I would say. Engineering is a little bit harder, but where you have these awesome things being done for science goals, you have a lot on the engineering side, what I call the dominoes of despair. And that is where you're like, well, it's a little bit harder now than it would be later, so let's stop. Or wouldn't that be a little harder than this? So why don't we do this? And it's this slippery slope where all of a sudden you get InSight that was meant to be 3 landers, and then it was 1 lander, and 1 lander wasn't actually able to really get into the depth of Mars like we wanted it to. And so as much as it's a great mission, I like it, it essentially failed at all of its goals. And it's because they took on what went from a very, very solid mission design with very little risk. They took on tons of risk through this, we can do it with a single unit. And then it's a single point of failure. And then there they are. So when people are asking about 1 or 3, I want to go with 3. I want to go, 5 years from now.
10,
We
12.
can do it from now. It's just, yes, it all depends.
Like
on,
Oprah, everybody gets an eel. You get an eel. You get an eel.
Well, actually, that's what it's looking like with all of our partners, right? As we start building them, they're way cheaper than the RoboSimians and the other ones we've built in the past. And we start giving them to our university partners. We start getting them into the hands of the Norwegian Space Agency and ESA, and we start getting, these simulation environments out there, and you see how excited people get and what they can do with it. And then for me, it's just devastating to be like, and I hope any of us live to see it happen, and that's out of our hands.
But we're doing our very best.
We are. Yeah. I don't ever want to go down that route, so I let other people do it. I'm gonna keep pushing for what we're actually capable of and try not to take less.
Me too.
Well, marvelous talk, marvelous concept. I guess you've been very gracious with your time, and thank you for that. I suspect we probably ought to draw the meeting to a close. What I'd like to do is briefly mention our next session. The Greenway Talks will continue on Saturday, March 5th, when Caltech postgraduate scholar, Dr. Shreyas Visapragada, get that right, will return to the Greenway Talks to give us an update on his latest exoplanet research. A PD Saros Fellow and an NSF Graduate Research Fellow, Shreyas recently has observed the escaping atmosphere of exoplanet WASP 69b, has confirmed Kepler candidates using high precision ground-based photometry, and has developed computer simulations that model the emergence of chemical complexity in pre-planetary systems. He has been with us 3 times before, twice in an in-person talks. And much of the work that he does is on the 200-inch Hale telescope. So with that, thank you again to our speakers, Morgan Cable and Kalind Carpenter. And my thanks as well to everybody who came and participated to this meeting. Thank you for your support. Thank you for your participation. And with that, wave goodbye. Okay, everybody,
Thank you.
That's it.
So long.
So long, and I'm going to close the meeting down. Thank you very
Bye.
much.
Thank you.
Thank you.
Thank you.